we're now going to talk about resolving a vector into components. This is sort of the reverse process. Rather than starting with two vectors and combining them, here we're going to start with a single vector and split it apart, and this certainly has its advantages in certain problems. We'll define components as two perpendicular vectors that can replace the original vector. So you can see even the wording sounds similar. And we'll start with a simple problem. A soccer ball is kicked at 14 meters per second, 59 degrees above the horizontal. We're going to find the vertical and horizontal components. If this problem sounds familiar, this actually comes straight out of your summer assignment. But if it doesn't, that's okay too. So here's our original vector, which I drew in blue to make it similar to the previous problem. And here's our 59 degrees, which is above the horizontal. And the dashed line here represents the horizontal. So to make it into components, we make this into a right triangle. A component here in green that points strictly horizontal and a component that points strictly vertical, making a right triangle out of them. And these two green vectors are the components. I like to draw components as dashed lines. They're sort of imaginary. We're going to take this original vector and break it into two imaginary vectors, one that points strictly horizontal and one that points vertical. And I encourage you to do the same. Notice there are arrowheads on these component vectors, which is important. Here it's pointing to the right and up, which will come into play later on in a problem you might do with this. Now we'll identify the side of the triangle. Vy here is the vertical component, or in the y direction. Vx is the horizontal component, or in the x direction. And I call this Vl. This would be the launch velocity, the velocity of the soccer ball at the instant it leaves your foot. Let's say we want to find the vertical component first, and here's just a matter of using trig. Here's our vertical component, and we see how that is drawn in relation to the angle. We see it's the opposite from that angle, so the sine function is clearly the one we want. Where here sine of theta is Vy, opposite, over Vl, hypotenuse. First thing we want to do is rearrange, solve this for Vy, so Vy equals Vl times sine theta, and then substitute the numbers in, 14 meters per second times sine of 59 degrees. Make sure you take the time to write this out yourself. Then you type it in your calculator and you'll find that this component is 12 meters per second. Note there's two sig figs here because the angle measure has two sig figs, regardless of the fact that the hypotenuse has 3 sig figs. This 2 sig figs limits your answer. Think through what you would do for the horizontal component. Maybe pause the video and try it on your own. Here, since the horizontal component is the side adjacent to 59 degrees, I'm going to use cosine. So cosine of theta is adjacent over hypotenuse, Vx over Vl. Vx is going to be Vl times cosine theta. Substitute the numbers in, and you get 7.2 meters per second as the horizontal component. Let's see if this makes sense. 59 degrees is larger than 45 degrees, so we should expect the vertical to be larger than horizontal, and certainly the math bears that out as well. If for some reason you get the opposite results, maybe you want to check your drawing or just go back and see if you've drawn the angle in the proper place, but whatever it is, it should make sense. Here, the vertical is clearly larger than the horizontal, and the math shows that as well. And the reverse side of this page has more information about vectors in terms of reference angles and some common triangles you want to be familiar with that pop up very often. So I want you to familiarize yourself with all those things. And we'll certainly be doing a lot more in class with vector addition and resolving vectors into components. Thank you for listening.